Your production database goes down. You have a 500 gigabyte PostgreSQL cluster backup, but the specific application database you need to recover is only 5 gigabytes. Restoring the entire half-terabyte cluster just to retrieve those 5 gigabytes takes hours. In many cases, the target recovery machine lacks the physical disk space to hold the full backup, making a standard recovery impossible. pgBackRest addresses this with a specific flag, --db-include. You append it to your restore command and specify exactly which database you want to recover. It is often assumed that this command extracts only the target database from the backup archive and ignores the rest of the cluster. However, the restore process actually recreates the entire cluster structure. For the databases you exclude, pgBackRest writes them to disk as sparse, zeroed files that consume almost no physical space. Because these excluded databases are hollow shells, any attempt to connect to them after the restore will result in a fatal relation mapping error. Understanding how this design works is the difference between a successful emergency recovery and assuming your cluster is corrupted during a high-pressure incident. To see this in practice, we'll use a primary Postgres cluster containing 2 user databases, test1, which contains populated tables, and test2. In this scenario, disk space is limited, so we need to execute a selective restore for test2 while excluding test1. The first step is to use the pgBackRest info command with the --set option. This allows you to inspect the specific backup manifest you intend to use. This command displays the object identifiers, or OIDs, stored in the backup. Here we see Postgres 5, test1 32768, and test2 32769. The core system templates, Postgres, Template 0, and Template 1, are always part of this list. Postgres requires these to function, so pgBackRest includes them in every restore by default. Identifying these specific OIDs ensures you are targeting the correct database structures before initiating a partial restore. After stopping the cluster, you run the restore command and include the flag --db-include equals test2. On the disk, test2 and the system templates are written normally. The excluded database, test1, is created as a 0-byte sparse file. This creates a conflict with Postgres internal page consistency checks during the recovery sequence. As the system reaches consistency, Postgres inspects files in the cluster directory. When it encounters zeroed pages for test1, it flags severe block errors and stops recovery. To complete the process, explicitly tell Postgres to ignore these empty blocks. This is done by adding the --type equals immediate flag to the restore command. For PostgreSQL 13 and newer, you can also set Ignore Invalid Pages in your configuration. Without this override, PostgreSQL's self-preservation mechanics will interpret the sparse files as corruption and prevent the cluster from starting. With the overrides in place, recovery finishes and the cluster starts. The target database, test2, is fully operational and its data is accessible. However, PostgreSQL applies write-ahead logs at the cluster level. This means it replays transaction logs across every database in the system, including the sparse files for the excluded test1. Since the files for test1 are zeroed, PostgreSQL applies these incremental wall updates directly to the empty blocks without error. This results in a file structure that has recent transaction logs on its exterior, but contains no actual base data at its core. If you look at the cluster catalog, test1 appears to exist. But if you attempt a standard PSQL connection to verify its contents, the server rejects the attempt. The resulting error states that the relation mapping file contains invalid data. This is a design requirement. Allowing a connection would let an application query a database where the only valid information is a small amount of wall data, leading to incorrect results. This connection failure is a protective measure. It isolates your valid target database from the empty remnants of the excluded databases. The primary goal of this entire process was to save disk space on the target recovery machine. We can quantify the results by looking at the physical disk usage of test1. Before the restore, it occupied 7.4 megabytes. After this selective restore, its directory size is exactly 8.0 kilobytes. Those 8.0 kilobytes consist only of the minimal write-ahead log data written during the recovery phase. While the space is saved, the invalid shell of test1 still remains in the cluster's catalog. pgBackRest does not remove this automatically. A database cannot be dropped while the cluster is in recovery. The system must be fully online before the catalog can be modified. The final step in the recovery runbook is to manually execute a drop database command for test 1 to remove the invalid OID from the system. By querying the PG database table, you can confirm that only test 2 and the required system templates remain. A selective restore is a two-phase process. First, the space-saving extraction of your target data, followed by the manual removal of the holodoc shells to ensure the integrity of the cluster.